Hello, thank you for watching this video. So, on this video, I'll be doing question 6, which is Doppler effect of November 2020 question paper. So, this diagram that is drawn here is from the question paper. So, I drew it here so that I can make it easier to explain. So, I'll start the question and we can start. So, question 6. I'll read the statement like previous videos. As I'm reading the statement, I'll show the question paper so that you can pause, read for yourself if you're not happy with my reading, and do your own analysis or maybe attempt the question before watching this video. So I'll start reading now. So I'll start reading the question. So the question reads as follows. The siren of a train moving at a constant speed along a horizontal track emits sound with a constant frequency. A detector placed next to the track records the frequency of the sound waves. The results obtained are shown in the graph below, which is this graph here. So I will try to read the statement again. The siren of a train moving at a constant speed along a horizontal track emits sound with a constant frequency. A detector placed next to the track records the frequency of the sound waves. The results are obtained as shown below. So let's go to the questions. So this graph here shows the graphical representation of the sound waves that are detected by the detector. So let's go to the questions. 6.1. State the Doppler effect in words. So they want you to state the Doppler effect. So essentially they are asking you, what is Doppler effect? So as you might know, or let me not assume that. So Doppler effect, I'm going to explain the phenomenon and then define it. So when you're talking about Doppler effect, okay, let me first define it. So Doppler effect, it is an observed change in frequency of a sound that is caused by the difference in velocity between the source of sound and the observer, or the listener, or the detector in our case. So now, if you have a source of sound and you have a detector, and they have different velocities, so the observed frequency that is being emitted is going to change. So you're going to notice the change in frequency of a sound. So that is Doppler effect. So what causes this is, what causes this change in frequency, as I said, it is the relative motion or the velocity difference between the source of sound and the observer. So you know that the siren of yours in this case, which emits the sound, it emits sound waves, right? So now, if the siren or the ambulance or the train in this case, which has the siren, is approaching you, so the sound waves that are being emitted by that train, more sound waves will reach you per second if that train is moving towards you. So the sound will be compressed and reaches you at a higher frequency, which is why the frequency that you'll hear or you'll observe will be higher. But now, if the train is moving away from the detector or from the listener, now the sound wave that will reach the detector at longer time intervals. So there will be fewer sound wave that will be reaching the detector per second. So now the observed frequency will be lower. So now, if the source of sound is approaching you, then you'll observe a higher frequency. If it's moving away from you, then you will observe a lower frequency. So the source of sound can also be stationary. But then if you're moving towards it, you will observe a higher frequency. If you're moving away from the source of sound, you'll observe a lower frequency. So the magnitude of this frequency is okay. So now, because you're moving away from the source, I said that the frequency that you'll observe will be higher. Will be lower. And then if you're moving towards, it will be higher. So now, if the source of sound is stationary and the observer is stationary, the frequency that will be observed will be the same. because now the waves will be reaching, the sound waves will be reaching the detector at the same rate, at the same frequency. So now, once we start having the relative motion or the difference in velocities of these two, the source of sound and the listener, that's when you're going to observe the Doppler effect. So now, if you're defining Doppler effect now, you say it is the observed change in the frequency of a sound that is caused by the velocity difference between the source of sound or the observer, or is caused by the relative motion between the source of sound and the observer. That's the definition of Doppler effect. So I'm going to write it down. So now, Doppler effect is the observed change in frequency of a sound due to the relative motion between the source of sound and the observer or the detector in this case. This is the definition of the Doppler effect. So let's go to the second question. 6.2. 6.2 read as follows. Does the detector record the frequency of 3148 Hertz when the train moves towards or away from the detector? I'll read the question again. Does the detector record the frequency of 3148 Hertz when the train moves towards or away from the detector? So now, these are the detected frequencies. This 3148 Hertz and 2073 Hertz. So now, they are asking you, does the detector record this frequency, this 3148, as the source is approaching or moving away from the detector? So as I said when I explaining Doppler effect, so this one, the higher frequency, so when the source is approaching the detector, there are more sound waves that reaches the detector per second. So now the wavelength is shorter between the emitter sound waves. So now the frequency will be higher. But then if the source of sound is moving away, then the wavelength will be longer and the frequency observed will be lower. As a result, the higher frequency is observed as the source of sound is approaching the detector. So now, read the question again. Does the detector require the higher frequency when the train moves towards the detector or away from the detector? It requires this higher frequency, this 3148, when it is moving towards the detector. So in this case, it should be towards. Should be towards the detector. So the higher frequency will be recorded when the train is moving towards the detector. Straightforward. Then we go to 6.3. 6.3, calculate the speed of the train. Take the speed of sound in air as 340 meters per second. What do they want you to do now? They want you to calculate the speed of the train and take the speed of the sound in air as 340 meters per second. So now they want you to calculate the speed of the train. So what is our formula for Doppler effect? So we know our equation for this phenomenon is, so 6.3 is frequency of a listener is equal to speed of sound in air plus or minus velocity of a listener divided by velocity, or speed of sound in air plus or minus velocity of a source times the frequency of a source. This is our formula, Doppler effect formula. So now they want us to find the velocity of a source. This is what we need, or this is what we are asked to calculate, right? So we do have the frequency of a listener when the source was approaching us, which was 3148, the higher frequency. It was the frequency of a listener. And we have the second one when the source was moving away, the lower frequency, which was 2073 Hertz. we do have the speed of sound in air, which we're told that we should take it at 340 meters per second. We do have the velocity of a listener. The listener was the detector, and our detector was stationary. So we do have this. We do have this because these two are the same, which is the speed of sound in air. This is what we are told to calculate, right? The velocity of the source. But we also don't have the frequency of the source. We're not told what the frequency of the source was. We're only told the observed frequency, the one that was detected by our detector. So it's not our original frequency. It's not what the actual frequency that was emitted by the source. So what do? We say, okay, now let's list the information that we have, right? Let's list the information that we have. We say, okay, we do have the frequency of a listener. So when our train was approaching, let's say approach. So when our listener, our source of sound was approaching, we had the frequency of a listener. It was 3,148 hertz. This was our frequency of a listener. What else do we have? We have V, which is the same as this one. The speed of sound in air, which we are told to take it as 340 meters per second. Right? We do have the velocity of a listener. The velocity of a listener is 0 meters per second because our listener is our detector, and we know that our detector is stationary. So the velocity is 0 meters per second. We don't have the velocity of a source, which is what we are told to look for. We also don't have the velocity of frequency of a source. We also don't have the frequency of a source. So we are missing these two variables. But we don't need the second one. We are asked to calculate that one. But now, if we substitute all our known information, we'll have these two unknowns here. It would have been nice if we had the frequency of a source, because we'll be left with one unknown to solve for. But this is not the case. We have two unknowns. So now, because we have two unknowns, this information will not be enough to solve, for us to find the velocity of a source. Because, okay, so let me show you why it won't be enough. So this, in this case, our source of sound, which is the train, is approaching the detector. So now the observed frequency will be higher, as we know. That's why we took 3,148 is the higher frequency. So now what we're going to do is going to say, okay, what are the signs that we're going to use here? Plus or minus, plus or minus. That's the information that now we need to decide on. Are we going to have minus at the top, plus or top at the top, or in the numerator? The denominator is going to be plus or minus. That's what we are now going to sort out, and then start working on finding our velocity of the source. So we say, okay, frequency of a listener is equal to VL. I'm going to leave the signs. I'm going to come back to this. VS times the frequency of the source. So, because our source of sound is approaching, we know that the observed frequency will be higher, which means our numerator should be big. So we're going to have a positive here, so that our numerator is very big, and our denominator to be very small. Going to have a minus there. So if the source of sound is approaching you, you are going to observe a higher frequency, which means now your numerator of this equation should be big as possible. So now that's why you're going to have a plus at the top, and at the bottom you're going to have a minus, right? And then now you can substitute your known information. This is how you decide these signs. So if the source of sound is approaching you, you are going to have a higher frequency. For you to have a higher frequency, at the top you should have a bigger numerator at the top of our equation, which is the numerator. The numerator will be big as possible. That's why you have the positive. At the bottom you have small denominator. That's why you have a minus. So now let's substitute the information that we have. The frequency of a listener, what is it? It's 2148 is equal to speed of sound in air, 340, minus frequency of a listener, velocity of a listener, which is 0, divided by velocity, speed of sound in air, which is 340, minus velocity of a source, which is what you don't know, times the frequency of a source, which you don't know. This is what we want to solve for. But because we have another unknown, it's difficult for us to solve for the velocity of a source. So now, to sort this issue that we have here, we should use the second information that we have, that we are given. Because we are given the observed frequency as the source of sound was moving away from the detector. We are going to use it in a similar manner as this one. So we should collect all the information that we have, and then we are going to have these two still as unknowns. Then we can solve for the frequency of a source and velocity of a source simultaneously. This is how we are going to tackle this. So we're going to take this as the first equation. So let's go to the second part of our question. Or let's use the second part of our information, which is now the information that we have as the source of sound is moving away from the detector. So what information do we have? Let's go to that side. So now, okay, the frequency, our equation for Doppler, frequency of a listener is called the speed of sound in air, plus or minus velocity of a listener, over V plus or minus velocity of the source, times the frequency of the source. So now, our source of sound is moving away. It's moving away from the detector. So what do we have? We have the frequency of a listener to be 2073 Hz. We have the speed of sound in air to be 340. V is equal to 340 meters per second, speed of sound in air. And we have our velocity of a listener to be 0 meters per second. We don't have the velocity of the source. We also don't have the frequency of the source. So these are the two unknowns that we still don't know, we still don't have. So now, like in the previous question, we're going to substitute the information that we have and see what we don't have. So now, to substitute on this equation, which is your Doppler equation, the first thing that you should do is to set it up such that it tells you that the source of sound is moving away from the detector. So we're going to say, okay, frequency of a listener is equal to V, VL, velocity of the source times frequency of the source. So now what do we do? So we're saying that the source of sound is moving away. So now the observed frequency is lower, which is why it is 2073. When the source of sound was moving out towards the detector, it was higher, it was 3148. So now, if we want to obtain a lower frequency, which means we must have a bigger denominator and the smaller numerator. So in this case, if we want to have a smaller numerator, it should be minus here. And we want to have a bigger denominator to observe, to get a smaller overall product of this ratio here, and of this fraction actually, and the frequency of a source, we will have plus here. So the numerator will be very small and the denominator will be very big. So now that we have solved this, we should start substituting our known information. So what do we know? We know the frequency of a source is 2073 is equal to 340 minus velocity of a listener which was stationary, our detector, divide by 340 plus velocity of a source times the frequency of a source. So now, like from the previous equation, from the previous page, we still have those two unknowns. Then we can solve this equation simultaneously. So now the only thing left to do for us is to simplify this equation and simplify the previous one. So let's go simplify them. So we have two equations. I'm going to write both of them. So the first equation was 3148 is equal to 340 times Fs divide by 340 minus velocity of a source. This was the first equation. The second one is, the second equation is 2073 is equal to 340s F times Fs divide by 340 plus velocity of a source. This is your second equation. So like you do when you're doing solving simultaneous equation, you'll find the third equation from this one or from this one, whichever that you prefer. So let's find the third equation from the first one. We say, okay, cross multiply this times that, you're going to have 3148 times this bracket here, 340 minus Vs is equal to 340 Fs. So you have your 340 Fs to equal to this, which means now this is your third equation. This is your third equation. So now what you're going to do, we're going to say, okay, we have 340 Fs to equal to this, which means now you're going to sub, because since this equation is a simplification of the first one. So now you are going to substitute this third equation on the second equation. You're going to substitute the first equation on the second equation. So you have 340 Fs, you're going to substitute it here as this, which now on the second equation, when you see 340 times frequency, you're going to substitute this part here. So let's do that. So you do this by saying, okay, 272073 is equal to 340 Fs, which is equal to this. So we're going to say 3148 into 340 minus Vs divided by 340 plus Vs. So this equation here, you only substitute the third equation on the second one. The third equation was a simplification of the first one. So now you're going, it's more like a substitute the first equation on the second one. But you went to simplify it further to make it the third one. So what do we do here? You cross multiply here, you're trying to solve for Vs now. This times this, so you have 2073 times 340 plus Vs, which is equal to 3148. 34 times 340 minus Vs. 340 minus Vs. So now you simplify this straightforward from here. What do? We say, okay, this times this, 2073. We say 2073 times 340 what do we have? We have 704,820 plus this times that, which is 2073 Vs, is equal to this times that, 3,148 times 340, 3,148 times 340. What do we have? We have 1,070,320 minus 3,148 Vs. So now take like group, take the Vs to this side, transpose Vs to the left, and transpose 700,000 to the right. So what do we have? We have 2073 Vs plus 3,140 Vs is equal to, transpose this to that side, you have 1,070,320 minus 704,820. So we simplify this, you add these two, 2073 plus 3,140. What do we have? We have 5,213 Vs, which is equal to what? Say 1,070,320 minus 704,820. What do we have? We have 365,500. Then you divide by 5,213 on either side, 5,213. So you're done with question 6.3. So now we go to question 6.4. Let's read question 6.4. 6.4 reads as follows. The detector started recording the frequency of a moving train siren when the train is 350 meters away. Calculate the time t1. The detector started recording the frequency of a moving train siren when the train was 350 meters away. So our detector started recording the frequency of this train when the train was 350 meters away. So if we have our detector here and our train here, so this is our train. So the detector here, our detector started recording when this train was 350 meters away. That's what they are telling us. We're given that our detector here started recording when the train was 350 meters away. Calculate the time t1. So now they want you to calculate the time at which t1. What is t1? Let's go back to our original drawing. Let's go to T1. So T1 is this time here. So now it's when the frequency is, this is when at T1, this is when the train is passing the detector, T1. So now after it has traveled 350 meters. So now they want you to calculate the time it took from where the train was to pass the detector. That's what they want you to find, which is this time here. The time it took from when the detector started recording to when it passes, because at T1, this is when the train is moving away from the detector. So at T1, the train is moving away. But here, when the train was here, it was 350 meters away. So they want you to find the time it took for the train to move from where it was to where to pass the detector. So to do this, you say, okay, we know that distance is equal to speed times time. You do have the distance, that is 350 meters away. You have the speed of the train, that is 70.11 times time. So you are solving for time. So you divide by 70.11 divided by 70.11. So your time, which is equal to T1, is equal to 350 divided by 70.11. 350 divided by 70.11. So this is 4.99 seconds. So the train took 4.99 seconds to travel 350 meters and pass the detector. So it took 4.99 seconds, which is more or less 5 seconds. This is where this question ends. This was easy 11 marks.